Good morning everyone. My name is SATHWIK. I am from CSE-C section and my topic is DNA-like materials could open new computing frontiers. As computers have progressed over the last few decades, with their component transistors getting even smaller and ever more numerous on a single chip, the relentless progress famously described by Moore's law has begun to bump up against fundamental physical limits to what can be done with the present etched lines on silicon technology. But now, a new twist involving an organic molecule that has DNA-like helical shape may provide an alternative pathway that could shrink transistors down to atom-sized scales, and even DNA molecules themselves might ultimately become the bits and bytes and logic gates of the future. Transistors are the fundamental building blocks of computer chips, just as proteins are the basis of living organisms. They are essentially just sophisticated on-off switches whose state can be flipped from one to the other by applying an electrical signal, or boosters that can amplify a signal arranged together in complex circuits. They can store the ones and zeros of computational data or carry out the basic logic functions and or etc. that can underlie all computation. The first computer chips had dozens of transistors on them, but nowadays they each contain billions. But the constant shaving down of sizes of transistors and wires that interconnect them on a chip have now made them so tiny that random quantum effects are beginning to limit any further shrinkage. Using rare earth metals, tellurium, the team found has a highly unusual property. Unlike so-called two-dimensional materials such as graphene and boron nitride, which naturally forms into sheets just like a single atom or too thick, that have unique properties under special conditions, tellurium can form into what are essentially one-dimensional forms, single atoms in kind of daisy chain, each holding onto one other neighboring atom and forming a stack of slightly offset pairs. And that's where the twist comes in. These signal chains, arrays of tellurium atoms, don't form a straight line. Rather, it forms a stack of pairs that naturally twist into a helical form, reminis- reminiscent of DNA molecules or the steps of spiral staircase. But unlike DNA, which goes only one way, tellurium has no preference for whether the helix turns clockwise or counterclockwise, so the two forms are produced in equal measure. Tellurium, being metallic and naturally conductive, when encased in a nanotube or nanoconductive material, for which he and his team used boron nitride, the pairs of materials from a junction that can act as field effect transistor. The entire transistor structure can be just 2 nanometers across, while today's smallest silicon transistor range from 10 to 20 nm. Many teams around the world are working on wide variety of ultra-thin metals, ECs, in hopes of finding replacements for the silicon in microchips that increasingly are at the heart of nearly everything we use, from smartphones and laptops, computers to biomedical diagnostic and treatment devices to smart thermostats, appliances and light bulbs. Carbon nanotubes are conductive. However, the original configuration of tellurium chains inside carbon nanotubes would not allow for functioning transistor, which would need to be electrically isolated from its environment. To form functioning transistors, the 1D tellurium chains would need to be grown inside non-conductive casings. Instead, fortunately, there is a such thing. Yokin App at Michael Technological University provided a variety of nanotubes made of boron nitride and naturally insulating compound that readily forms 2D sheets and nanotubes. These nanotubes took place of carbon-based ones, and tellurium chains were grown inside them. While trapping a single tellurium 1D strand would require a nanotube just 0.8 nm across, the boron nitride nanotubes they use only go down to about 2 nm across. For testing, involved tubes containing several strands rather than just one. While bigger than the ideal single strand helix transistor, the multi-strand version is still small enough to handily beat other transistor technologies in the race to bottom in scaling down microchips. DNA origami. Teams around the world continue to explore yet another alternative to silicon for smaller and faster computers. The possibility of using DNA molecules themselves for computation. This would take advantage of some of the built-in capacity for replication of self-repair that these biomolecules offer. Such efforts have been going on since at least the 1990s, with much interesting research but so far no clear application that provides advantages over other materials. Researchers at Israel's Weizmann Institute produced some of the earliest DNA and enzyme-based computers, and in 2004, Ehud Shapiro and a team of other Weizmann made a DNA computer capable of assisting with cancer diagnosis. By 2013, researchers succeeded in storing large amount of data in the form of DNA storage. Research continues towards truly reversible, flexible computational tools making use of DNA, but the goal has remained elusive. Lab-scale devices have been developed, but nothing has yet reached commercial application. The quest continues, though, because theoretical calculations have shown that in principle an amount of DNA-based material smaller than typical PC could be many orders of magnitude faster and store others of magnitude more data than all computer evils built. But some research have estimated. John Reff, a distinguished professor of computer science at Duke University, is one of the leaders in this area of research. His recent work has focused on fast and compact DNA logic circuits, DNA-based digital data storage, DNA barcodes for single molecule fingerprinting, and DNA-based analog computing. Some of this research is focused on using the ability of DNA molecules to bind to one another to create complex shapes. These can aid in diffusion process of DNA strands, which is one of the limiting factors in DNA computing. Though the diffusion is very slow by computing standards, it is counterbalanced by the extraordinary parallelism made by its tiny, easily replicable molecules. A whole field of DNA origami has been arisen using shapes constructed from DNA chains as a way of speeding the diffusion process and many other functions. In principle, DNA computing could have many advantages. The material itself is abundant and cheap, and unlike many of the materials now used in microchip manufacturing, there's nothing toxic or hazardous about it or the materials used to handle it. And in principle, it can beat just about anything in terms of computational power of given weight or volume. Last year, for the first time, a DNA computer was demonstrated by Professor David Doughty at the University of California at Santa Cruz that could actually be reprogrammed. Until then, every DNA computer was hardwired with its instructions and could only run a single algorithm, Doughty said, but the new device opens the door to potential multi-purpose DNA computing. Doughty suggested the programmable DNA devices could be used to program DNA robots, which in turn could be used, for example, to target specific cancers in the body. The research described last year in Nature is still very basic and extraordinary, and far from any practical application, but it is perhaps the most promising sign so far that untapped potential of DNA computing might be on the horizon. Whether it's in the form of some kind of reprogrammable DNA based computers or in the form of transistors made from elemental materials whose natural structures mimic those of DNA molecules, it seems likely that some kind of helical molecules will be playing an important part in the future computation and electronics. And this is the end of the Tech Talk. Thank you.